Sir, the Nora?
Hello.
Sir, good morning, sir. Good morning. How are you, sir?
Morning to you.
Fine, fine, sir.
How are you?
Fine, sir. Fine.
Sir, Vaidya sir.
Yes, sir.
Sir, he is my head of the department, sir.
Yes, sir.
Dr. R. Naidu is head of the department, sir.
Yes, sir.
Naidu.
Yes,
Thank you, Dr. Naidu. Thanks for having me.
Welcome, sir. Welcome to the session. Yeah?
I hope everybody is well. All your family, everybody is doing
Yes,
well.
sir. Fine, sir. What about you, sir? Yesterday we heard about that a big storm is there. Storm was there. Today is everything fine, sir? Today everything fine?
Things are yesterday the storm was quite bad after
Yes.
a long time.
Yes,
To meet like that.
Yes, sir. Now it is
so,
okay.
Now it's okay. Yeah. Today it was okay.
Yes, sir.
And then
Sir.
sorry to mess up your schedule.
No problem, sir. It is not your fault, no. It's nature's fault.
Sir, what about
nature's
yesterday we heard about the storm is there. Storm was there.
Sir, with your permission, sir, shall we start? Sir?
Today everything fine.
Shall we start, sir? With your permission.
Yeah, sure. Anytime. Whenever you're ready. Yes.
Okay, sir. Murali,
Sir.
please introduce our today's resource person,
Okay.
Ashwin Vaidya.
Thank you. Thank you very much, sir, Dr. Arland, sir.
Welcome.
It gives me an immense pleasure to introduce today's speaker, Professor Ashwin Vaidya. He is an associate professor, Department of Mathematical Sciences, Montclair State University, New Jersey, United States of America. So, Professor Ashwin Vaidya obtained his Bachelor of Philosophy in Physics, Astronomy, and Mathematics in 1995, and then Master of Science in Physics in 1998, and then Master of Science in Mathematics 1999. So, from University of Pittsburgh. And again, he obtained his doctoral degree in 2004 from University of Pittsburgh. Since then, he had been worked as postdoctoral associate from Carnegie Mellon University and research associate from Florida State University, and then again postdoctoral instructor from Florida State University, and after that RKG postdoctoral research associate from University of North Carolina. Professor Vaidya worked as assistant professor, Department of Mathematical Sciences, Montclair State University from 2009 to 14. Also, he was director Science Honors in Innovation Program for College of Mathematics and Science, Montclair State University, from 2014 to 18. From 2014 onwards, he has been working as an associate professor, Department of Mathematical Sciences, Montclair State University. In the period 2016 to 17, he was auxiliary chair, Department of Mathematical Sciences, Montclair State University. From 2018 to present, he is an associate professor, joint appointment, Department of Physics and Astronomy in Montclair State University. At present, he is the chairperson, Department of Mathematical Sciences, Montclair State University. His research interest covers a wide variety of subfields of fluid mechanics, including Newtonian and non-Newtonian fluids, fluid structure interactions, biofluid dynamics and hydrodynamics stability. He has also published papers on subject of non-equilibrium thermodynamics, pattern formation, nonlinear dynamics, network analysis, and philosophy of science. Professor Vaidya has authored nearly 50 more journal papers like highest impact factor, physics of life reviews, which is having more than 11 impact factor, as well as the computational and applied mathematics, International Journal of Nonlinear Mechanics, physics letters A, International Journal of Nonlinear Mechanics, applied mathematics and computation, physical D, nonlinear analysis, mathematical methods in applied science, etc. And also he authored for some book chapters of complex fluid flow. He currently serves on the editorial board of the journal Applied Mathematics and Computation, published by Elsewhere, of course, and in some other journals. He is a review for various journals in different publishers like Elsewhere, Taylor and Francis, Springer, Hindua, etc. Professor Vaidya gave several talks on various national and international forums. He was invited as a speaker for the GYAN program of lecture series on mathematical theory of complex fluids, Department of Mathematics, National Institute of Technology, Kurukshetra. At last, I proudly say that Professor Ashwin Vaidya is external international review for my PhD dissertation. I thank to him. Now I request Professor Ashwin Vaidya to deliver his lecture.
Sir, please proceed. Thank you, Murli.
Thank you so much, Dr. Naidu. Thank you so much, Murli,
Yes,
for the invitation and for such a warm welcome.
it's our
and
pleasure,
for the
sir.
introduction.
Pleasure,
I'm
sir.
very
And
happy.
happiness.
Very happy, and I hope someday when the
Yes.
pandemic is over that we get to meet in person.
Sure, sir. Sure, sir.
So let me just share my
Yes.
talk. Please tell me if you can see this. You can see this, right?
No, sir. Presentation, not it, sir. Yeah, now it's okay, sir.
No.
It's okay, sir.
So I was happy to hear about the topic of your of the whole workshop.
Faculty development program.
The importance of mathematics and science and technology. I think it's nice to have
Yes,
a
sir.
wide topic like this.
Yes, sir.
And there's so much to be said. You can't cover obviously all of this in 1 week.
Yes,
Take us years to talk about these things.
Yes.
What I thought I will do is, I've realized in the recent years that much of the work that I do falls under this general area called complex systems. Complex systems covers a lot of ground. People from disciplines of mathematics, and physics, and engineering, even in disciplines like political science and sociology and philosophy and economics, you can encompass all of that and bring it under the subject of complex systems. And it truly talks about the importance of mathematics. I mean, discussion here is focused on mathematics and science and technology, but the importance of mathematics goes far beyond some of that. I think it's the power of the language. It's really the beauty of mathematics. Hopefully we get to appreciate it. So I am not quite sure how many audience members are here. I think I see 5 or 6 in the list.
No, sir. In this room, we have not allowed, sir. Nearly 460 participants are there, sir. 460.
I see.
We have
I see.
allowed
Okay.
Cisco WebEx is given only for our personal purpose. You and myself and three more faculty members, sir.
So there are others who are
they are seeing in through YouTube's streaming.
I see.
Yes.
So, much of what I'm going to talk about today is all done with the help of collaborators. I've had several. I just listed a few here. I'll tell you more about what they've done, what we've done together. So this I just wanted to show you a little picture of my university.
Yes. Nice, sir.
It's called Montclair State University. Here's an aerial map of it. These days, Google Maps can do a very nice job. So we sit on the top of a hill in the state of New Jersey in the United States, which is right around here somewhere on the map. And we're very close to New York City, so we're only 14 miles from New York City. So hopefully, like I was saying, one day soon when things get better, we'll also get a chance to invite you to my department.
Thank you, sir.
So if you want to learn more about what is going on in the university and surrounding areas, feel free to go visit our website.
Yeah.
You'll see a little more about sort of the culture of mathematics within my department. Murali described this in quite a lot of detail. So my research and interests encompasses a lot of sort of a broad area, starting from fluid mechanics, but it has gone beyond that. I'm also interested in mathematics, of course, but also on doing experiments. So some years ago, when I was still a postdoctoral scholar, I got to work with some mathematicians who were doing experiments, physical experiments. They had a huge lab in their department, and it actually turned out to be a big plus to get an experience like this. Because you can, modeling is something that we do in the abstract, but when you actually touch and feel the physical system that you're working with, then your understanding of that system becomes at a completely different level. You can really appreciate and get very good ideas about the mathematics as well behind all of this. So the subject that I'd like to discuss today is complex systems. So if you look at a definition of a complex system, it's a system which is composed of many parts. It has several components, and each of these components interacts with each other. And that's what makes it complex. A system is something which has many parts, and a complex system is in which each part interacts with each other. So the climate, studying living organism, human body, power grid, transportation system, communication systems. All of these things are examples of really complex systems. And mathematics plays a big role in this. So what I want to do is give you some different examples of this in my own work. But overall, the kinds of tools that one uses, these are the things that we're familiar with. Right? We sometimes think of ourselves as experts in specific areas. You ask it, typically a mathematician what they do, they will say, well, I study nonlinear dynamics, I study networks, I study group theory, I'm a numerical analyst. But really, these are specific tools that are used, that came about because we need to solve more complicated problems. And so essentially, we're all part of small ants that are working towards building something big, the ant hill. And that big system is a complex system. Sometimes we realize it and we're working consciously towards it. Sometimes we don't even realize that we're contributing to bigger goals. So I just want to give you a glimpse of some of these things. If I have time, I always over-prepare, so I have too many slides, but let's see how far I can go. Hopefully I'll give you all a little glimpse of different tools that I've picked up and found useful along the way. So some important terminologies. Complex system is something which is, it's not complicated, it's complex. Mathematicians and scientists know that the best kind of science is one that is simple. But simple doesn't mean anybody can do it. Simple just means that that's the most efficient way of doing it. To find the most efficient takes a lot of practice, lots of years of hard work and study and all this. But so a complex system is a large system that's the simplest one that's possible, but it's complex because it's interconnected. But if it's a genuinely complex system, then there are certain features of it that emerge in time. One is called self-organization. In time, you get patterns. And there are certain driving features of complex systems that drive it towards these organized patterns. Beautiful patterns. And often our search in mathematics is to find an explanation to it. The other concept is that of emergence. And emergence refers to is to the structures that arise. Sometimes it is a picture of a snowflake. It's basically ice and water and temperature. But at a certain critical point, you get these sudden appearance of these special structures. These are called emergence. And so this is just a property of these complex systems. So in some ways, you can say that human life, all of us, are emergent structures in the cosmos. We are an accumulation of energy at the right time, in the right place, in the right way. And the universe gave rise to conscious being. So we are all emergent in something. We emerged from this chaotic mess of the universe. Because I cannot hear you in the background, just let me know that the system is still on. Right? You can hear me?
Yes, sir. Yes, sir. Yes, sir. It's clear, sir. It's clear.
Okay. Once in a while, I may just check.
Yes, sir. Thank you.
Thank you. So, I'd like to say one thing because I think going forward, I'd like to show you, talk a little bit about the mathematical problems that I've been working on, but especially in the context of engineering and biology, I had stated. But I would also like to discuss the importance of experimentation. There are different kinds of experiments one can talk about. One is experimenting with mathematics itself, and which is being willing to be wrong, willing to take chances, willing to try new things. You can't jump to the final answer right at the beginning. It takes many tries. But that's one kind of experimentation. The other kind is a real physical experiment. So this is what I mentioned before, that I actually have a lab as well in my department. We call it the Complex Fluids Lab. And we perform physical experiments. In some ways, it's very easy to get students involved in. So it's a learning experience as well. But the beauty of applied mathematics in particular is a deep mystery. We don't know why mathematics even works in the universe. Why is the universe so logical? But the second question is, the beautiful part is you can take whatever is out there in the universe and you can bring it down to the level of a small table. So, you know the famous fictional story of the apple falling on Newton's head and things like that. Apparently, it's not true. The point behind that story was, I think, the discovery of gravity. Essentially pointed to the unification of what happens outside the universe, the global phenomenon. Gravity is a global event, it's a universal event, holds galaxies. But at the same time, it can even explain simple things like an apple falling. So, stars and apples essentially all have to obey the same laws. So, the point I'm trying to make is the value of an experiment is that you can play around with things that you cannot otherwise even imagine in your life. Systems can be very complex, but in doing a simple experiment allows you to simplify and then build simpler models, which you can then slowly expand out. So, doing good mathematics, I learned from good mathematicians is a lot of patient work. It's years of work, and often you encounter more dead ends than not. Another value of doing experiments is you get to collaborate and you get to think. Mathematicians think a particular way, but people who perform experiments, people who work with physical devices think very differently. But you're trying to solve the same problem. I think the trouble is sometimes we get stuck in trying to solve a problem in one way. There are many solutions and many ways to think about that. And so I think just talking to other people, collaborating, those, they make for wonderful experiences. They are very interesting and fun conversations. We also learn something very meaningful when we talk about it. So what I want to talk about today is, see how much time I have, but I want to give you a few examples of complex systems and the kinds of mathematical models that seem to appear when you solve them. So I cannot say that I'm an expert in this field. Most of my research work is in the area of fluid dynamics, but I would prefer not to think of myself as a differential equations expert or this or that. You learn whatever you need to learn to solve the problem. So the question is, what are we trying to solve, and what is the best tool for that problem? So I cannot force my tool on a particular solution, on a particular problem. So I'll try and go through a couple of examples, diverse ones, on sort of pattern formation in fluids and solids. There's a new project which it's not very new actually. It's working for almost 10 years now, but it's taken a new direction in a very engineering direction, energy harvesting. Of course, my side of it is more to then if I have some time, I'll tell you a little bit about some of the work we're doing in fluid dynamics in the eye, ocular fluid dynamics. And I'm very sure I won't have time for this. I'm also working on problems related to how proteins aggregate in the brain, related to things like Alzheimer's disease. So before we start, just a brief overview of fluids in general. I assume people here have some background in fluids, of course, maybe mathematicians in different fields. But a fluid is a gas or a liquid, and there are different ways to describe these. I'll stick to talking only about liquids. Gas is a little more complicated. One important feature of liquids is its viscosity. Viscosity is essentially the coefficient of the stresses that act between layers of the liquid. And so viscosity is, think of it as friction, and it's internal friction in a fluid, in a liquid. So we classify fluids according to, we could classify fluids, one way of classifying fluids would be according to kind of viscosity. And a typical liquid that one is used to, we call Newtonian liquids, water. Viscosity is a constant. It means everywhere in the liquid, it's a homogeneous liquid, and everywhere, and when it's moving, it has a certain viscosity. If it goes faster, it has the same viscosity. If it goes slower, it has the same viscosity, and so on. But in general, in life, the kind of liquids one encounters are not Newtonian. The Newtonian, so as in this picture, will show you, mu is the coefficient of viscosity. If it's constant, it's flat, and it's Newtonian. But often, as the system speeds up or slows down, its viscosity will change because the liquid itself may not be homogeneous, may not be constructed the same way everywhere. And also, with speed, the forces that rub between the layers of the liquid may change. So now, if its viscosity goes down with increasing shear, shear is the lateral forces between layers of the liquid. Then it's called shear thinning. Sometimes it gets viscosity goes up. It's a little more rare. It's called shear thickening. These kinds of liquids, shear thinning and shear thickening, are called non-Newtonian. They don't behave in a constant manner. Viscosity can change, and so these are far more complex liquids, and the resulting differential equations that one solves for are far more nonlinear. And then you also have other kinds of liquids called viscoelastic. So these are liquids which have not just complicated viscosity, but they could have added features like elasticity. So they have stretchy behavior. So some examples of these kinds of liquids. If you take a rod, if you're making buttermilk, for example, you add a lot of water to it, you dilute it. Then you take a rod and you turn it. What you would see is on the surface of the liquid, or even if you're stirring coffee, put your spoon inside coffee and you stir it. Pay attention to what happens. So let's take a spoon, here's a cup of diluted coffee. You'll see that the surface goes inside. But now if you take something like paint, and you try to mix the paint with the rod, and you just do this, house paint. What you might find is certain kinds of paint actually start rising up the surface. When you do the same rotation, the surface doesn't go inside, go inward. It actually comes outward. It starts to climb the rod. So this is called a rod climbing. So here, cornstarch, for example, is one of these things. And the non-Newtonian liquids have other properties too. They're very stretchy sometimes. So stretchy you can cut it. these are elastic liquids are somewhere between a solid and a liquid. Okay, so given that explanation, basic physical explanation, I'll tell you about one particular phenomenon. It's a very simple idea, and this problem has been studied for almost 150 years now. In the 1840s, 1830s or 40s, Kirchhoff, we all know him from his work in electricity, he wanted to understand how paper falls. When you drop a piece of paper, paper will settle very slowly as it falls down. But often you don't see this. Right? You see often swaying of paper as it falls. And in windy conditions, you might even tumble and do things like that. So the motion of falling objects is very complicated. You drop something as simple as a ball, in some ways you can predict the motion of the ball, but those are usually very simple conditions under which one can predict it very easily. It's a very complicated thing. So now assume you have something like a cylinder. You can hear me, I assume, right?
Yes, sir.
So
yes, sir. It's clear. Sir. Thank you.
Volume. So if you have these filaments, look at these filaments, and these are filaments that are falling in a very viscous liquid. What you see is if I start dropping this is an iron filament, an iron rod. As it falls vertically downward, but it's maintaining the same orientation as it falls. So the liquid here is glistening. Now, this is an experiment that I did when I was in Florida State University. There was a lab over there which had 8 or 10 feet high tank, which is full of corn syrup, sugar syrup. And so the background liquid you're seeing is sugar syrup. 10 feet high and cross-section area about 2 feet by 2 feet. So maybe 1 foot by 1 foot, but 1.5 feet by 1.5 feet. So it's a large volume of sugar syrup. It was used just for experiments. And here's a brass rod. So I dropped the brass rod inside it. It took about 2 days for it to fall all the way down. So it's almost got stuck in between. But the point I'm trying to make here is in this very viscous liquid, very, very thick viscous liquid, the orientation of something as heavy as a brass rod, very heavy. It's about 2 inches in length and about 1 inch in diameter. This would fall extremely slowly. And what happens is the orientation of this particle never changed. I dropped it like this, stayed like this, it would fall. So when you drop a ball in air, a ball has perfect symmetry. You don't have to ever think about what is the right orientation of the ball. But when you drop something which doesn't have as much symmetry as a sphere, then the question arises, what is the correct orientation of an object when it's falling? So there's some famous experiments done by this professor, Daniel Joseph, who's not alive anymore, in the early 1900s. I'm sorry, 1990s. So he dropped these capsules in a liquid which is a mixture of glycerin and water. Now, if you drop it, so this is time 1, time 2, time 3, time 4, and so on. If it is very viscous, then it would, whatever you started with, it will maintain that position. But if it is not very viscous, means you diluted it a little bit, you reduce the viscosity, then it seems to turn as it falls and eventually settles into a horizontal state. And this is the direction of gravity. So it's falling this way. In all these pictures, it's falling downward. Now, so it seems of all the possible ways an object could orient itself, it is selecting this particular orientation. which means the direction of gravity is this, and it's orienting itself with this long axis perpendicular to gravity. So there's infinitely many orientations allowed, but only one orientation is possible, the stable orientation. Now look at this particular phenomenon. So here the liquid is now an elastic liquid. So you add a little bit of polymer in the liquid. The polymers have long molecules in them, and they give it a non-Newtonian effect. So it takes a while to make these liquids. It takes a little extra work. You have to add water, warm it up, mix it very well, let it cool down and settle. And once it becomes homogeneous, and it's then these experiments were done. Again, these are metal capsules, and it is dropped, and you can see, but it's falling vertically down. So this is the direction of gravity. And when you drop it, so here you can say that it's falling flat. But when you drop it in an elastic liquid, what seems to happen, it becomes vertical as it falls. It's completely opposite. So even here, only one state is allowed. Meaning, even if I put my finger inside and push it, eventually it will come back to the same state. Mathematically, one would say it is a stable configuration, a stable, steady state. So if you're trying to understand something which is physically relevant like this, then you have to first understand the physics behind this. What could be happening? You can't just use any kind of mathematics to describe this. You have to apply the right kind of mathematics. And it's just important to understand what is turning something. So if you start here, there's some sort of a force. Actually, in this case, it's a torque acting on the body. A body is immersed in the liquid. It's getting pushed in different directions on different sides. Eventually, it's arriving at this particular position, and it settles at this. That means from here on, at every other time, it will look just like this. This kind of a liquid, it will start in some orientation, but it doesn't like that position, so it shifts until it reaches a position where it is completely perfectly aligned and it's steady. So the point is, you have to figure out what sort of torques are acting on the body. Once you model the torques acting on the body, then you can figure out mathematically. I haven't got to the mathematics yet. I'll do that in a minute. I apologize if I'm delaying this. So when I developed my own lab, I wanted to redo these experiments in a slightly different way, because what happens is when you do any experiment in which objects fall, there's very little time to observe them. So experiments tend to be Can you hear me?
Yes, sir. Yes, sir.
All of a sudden I heard a sound, so I thought I lost it.
No, sir.
So we redesigned the experiment in such a way that I had this water tunnel, and the water tunnel looks something like this. So what I did was we designed a cylinder or something which had symmetries, lesser symmetries than a sphere. And water tunnel, so I know it's a little hard to see maybe. There's a little cylinder over here which is hinged. So it's hinged on a wire, on a rod. There's a little ball bearing inside. And all this is allowed to do is rock back and forth. So it has, the only possible motion is it can take on a particular position, but it can go back and forth and nothing else. Now, this is identical to the idea of something falling and orienting itself. Right? In this case, what we're doing is the water is still, but the body is falling. In an experiment like this, the water is flowing, so the liquid is moving. There's a pump here, which allows the liquid to flow left or right, but the body is fixed. The only thing you're allowed to do is change its orientation with respect to the flow. So here are some videos. I just want to show you this. So if this is relatively slow flow, so there's bubbles in here, that is what allows you to see these things. And you can see the particle is now oriented in a way. So the flow direction is this. And this is called vortex shedding. This is a special region that happens behind. So when the Reynolds number is a number that characterizes how much inertia there is in the system. So if you work in the area of fluid dynamics, this is a very important number you have. Okay. So at the Reynolds number is low, what happens is you will find that these objects, this object does not move. It's capable of going back and forth, but it doesn't move. The only thing that moves is it. Now here's another experiment. This is when the flow is going faster. And it's going faster, and what you see is the liquid is going fast. The object starts to go back and forth, back and forth, back and forth. So what happens is, if I track the motion of the particle, you find that it starts to oscillate. You'll see that as the flow, Reynolds number tells me, let's assume that it just tells me a little more complicated, it tells me the speed it will flow. It has information about the speed. As the speed increases, I can see the oscillations are getting tighter. It means the frequency is increasing, the oscillations of the particle are getting faster and faster and faster. It is very periodic, very periodic. In fact, there may be some multiple double periodicity over here. So we create this bifurcation diagram. Bifurcation diagram contains information about all the phases that the object can undergo. So this tells me, so this is plotted against Reynolds number is the speed of the flow, the inertia of the flow, and this axis over here tells me the inertia of the particle, meaning how capable is the particle of moving around. And this tells me how capable is the liquid of moving, going fast. So there's a competition between the motion of the liquid and the motion of the solid body. And there are regions where nothing happens. The object, the blue region is steady state. That means the particle stays fixed. It takes on a particular orientation, it stays fixed. Then there are these light blue regions, and the light blue regions tell us, the green one here, tells us when the object is capable of going back and forth, oscillating back periodically. And then the red regions, which are regions called autorotation. The object is capable of completely rotating. I'll talk about that. Alright, so for mathematicians will be happy to see this. The equations for the system are, write down the partial differential equation, which is basically the Navier-Stokes equation. So when you're writing down, the system here is a complex system. Why? Because you have two parts. One is a liquid, is moving. The liquid is described by this equation. U is the velocity of the liquid. Omega is the rotational, the angular velocity of the solid object, which is causing more disturbance in the liquid. E is a stress tensor, which describes the kind of liquid we have here. In this particular problem, it's a Newtonian liquid. And the stress tensor depends on the pressure and the viscosity and so on. And there's gravity that's in the system. So you have a nonlinear partial differential equation right here. And this describes the motion of the liquid with the appropriate conditions. Boundary conditions at infinity, etc. And then you also need the equation of the body. And this is what makes it complex, is that you have two systems. The system has two parts. It's a relatively, I would say, simple complex system. But it's a very sophisticated one because the liquid itself is complex. And to describe the liquid itself is a very difficult thing. But on top of it, you also have a body. So the liquid is moving the body is moving, and as the result of moving, the body is now affecting the liquid. So they're both affecting each other. And to write the equation of the body, you need the equation of forces, and you need the equation of torques. And these are there are a lot of unknowns in this problem, so it makes it a very difficult problem. Now, without going into details, I'll just tell you that you employ certain trick to figure out, if you want to understand how an object is oriented, all you have to understand is you don't need to solve this entire problem. So in some of our previous papers, we have looked at these problems, and we have, this is some of my very early work in my thesis. I was interested in existence and uniqueness of solutions to these kinds of systems. But later on, I became more interested in what I can do with these things, the applications of these. So if I'm only interested in understanding what the orientation is, then I simply have to understand how to write the torque on the object. The torque is the net sum of all the rotational forces on the system. And if I want to figure out what is the stable terminal orientation, the equilibrium position, then all I have to find out is when is the torque equal to 0. When the torque is equal to 0, the system stops to move and it just reaches steady state. So you can write down the torque. I'm not going into details here because each of these steps will take a very long time. I'll just give you an overview. You can write down the torque as a sum of various components. There is a component due to inertia. This is the Newtonian component. And then you can write down in general for any liquid. So if you have a very complicated liquid like a viscoelastic, there will be a component of torque coming from the inertia of the liquid, which contains information about the viscosity. And then there is a component coming from the elasticity. And these all happen to be integrals of complicated dot products of vector intensities. So it's the same, similar equation. And you can prove some theorem saying some of these terms are bounded, some of these terms go to 0. At the end of the day, I'll just tell you, it is possible using certain tricks is to write down the net torque on an object due to a fluid as a function of some complicated coefficients, which depend upon the material properties of the liquid, but also on the angle of the body. So you can write down, so there are some complicated coefficients here which have to be computed. But then you also get these terms sine theta and cosine theta. And this theta is nothing but this angle tells you information about the orientation. So if I now want to understand in the Newtonian liquid, which is like water, if the object is moving not too fast, but at a reasonable pace, and what this reasonable pace is based on, it's a little complicated to describe. But from experiments, we know that it should be maybe Reynolds number 10 or something like that. So here's the expression for the net torque imposed by the fluid, Newtonian fluid, on a body. So in this case, what you will see is for this torque to be 0, the only way this can be 0 is if sine theta is 0 or cosine theta is 0. And those are only possible if theta is 90 degrees or 0 degrees. And you will see the way angle is measured is with respect to some fixed axis on the body. So when theta is 0, right, that means the object is falling this way. When theta is 90, the object is falling this way. So the only way an object can fall is either along horizontal direction or a vertical direction. All right, so only two possibilities out of infinitely many possibilities, 2 are allowed. But just because 2 are allowed doesn't mean that's what happens in experiments. In experiments, you see in the Newtonian liquid is always this. You never see this. But this is giving us 2 choices, which means you have to do a stability analysis. And so stability tells you just because something is in equilibrium doesn't mean it's stable. And so it so happens in this case, we can show using the stability argument that in this particular problem, the horizontal orientation. If you take a viscoelastic liquid with something called a second order model, which used to be popular in the 90s, It's a simple model to work with, but for anybody else working in the future at this territory and using this model, there are more useful models that one can use. You can show again that the expression for the net torque in the object looks something like this. So it has more complicated coefficients because there are elastic properties of the liquid. These are all complicated integrals that have to be computed. Now again, you get sine theta, cosine theta, and again, this is telling you that the net torque to be 0, the angle must be 0 degrees or 90 degrees. All the object can fall this way or this way. But again, if you do the stability theory, apply stability theory, you realize that the angle allowed here, the stable angle, is the exact opposite from the previous case. So here's one instance of where mathematics comes in handy. This is a very simple phenomenon. We're talking about a very fundamental classical problem. You're dropping an object in a fluid. You're trying to understand how it orients. It may seem like a meaningless problem, but in some other ways, it's a very valuable problem. It's a simplification of some other very complicated things. And that's what I want to talk about next. So you can actually use this idea to build wind turbines. So there's this idea called autorotation. Autorotation is when a body starts to rotate. So you've seen windmills, you've seen turbines move, not a motor. Motor you plug into the grid and the electricity drives it. But we're talking about self-induced rotation. The rotation that happens only because of the environment. So you take your toy fan, right, the paper fan, and you put it in the wind and it starts to move. That's called autorotation. So the wind is driving it. So here is an experiment. So here's a video of very high Reynolds numbers, high speed flows. Certain bodies, not every body will turn, but certain bodies will. I'm not sure if you're able to see this. This goes very fast. So the object, this is a square cylinder. And at high speeds, it just starts to tumble, to rotate automatically. And that's because the driving pressure in the front and back and so on have reached the critical value, which pushes it. And it's not just oscillating, it's actually rotating. So this was the subject of a recent paper that we published last year. We've done some experiments and numerical studies on autorotation. This phenomenon is called autorotation. This is the rotation of any of a body about any axis. The body is symmetrical and exposed to uniform airstream and has to be maintained only by hydrodynamic moments. So here again, we did some experiments, different kinds of shapes and things like that to see when objects autorotate. And then we also did, so I collaborated with an engineer friend of mine who studies turbines. We built simple models of different turbines of different shapes. And actually we were able to generate electricity. So here's power with Reynolds numbers. So these objects start to auto-rotate, and if you design it, you have to know. So he built the turbine is connected to power. Now this is doing the opposite of a motor. The reversing, this becomes your motor, and flow is making it turn, and then as a result of that, you can generate, build this equipment. It's a simple thing to make actually. You can actually extract electricity out of this. And so this is, and we're trying to not just extract electricity, we also want to find ways of making these turbines more efficient. And what we found is a very interesting setup is that, so this is the same water tunnel that I showed you before. There's a little particle that's capable of rotating. So I put a little blockage in front of it, just a wooden stick in front of it, of different sizes. And depending on where I position it, I can get it to rotate even faster. So here is an example of something. If I don't have anything, the object will rotate. This is the RPM, rotational speed of this object as a function of flow speed. So if I increase the speed of the liquid, the air flowing, this will start to move, rotate fast. But if I put, for the same airspeed, if I now put a little blockage in front, the body starts to move, rotate even faster. It's even more rapid. So I can enhance this rotation by 300%. So we did some numerical simulations of this model. So we took rigid body embedded in a system. So this 2D finite element simulation. And we built a little blockage in front. We kept moving the positions of this blockage, the distance from the blockage, the height of this blockage, how much of the body you're covering, and so on. And we solved the Navier-Stokes equations. And then this is just water here. You can do it there, of course, it's much easier, but because we do experiments to compare with water. We solve these equations, and one other thing we did is these are static simulations. So we're working now on dynamic ones where the liquid is capable of moving, but the body is also moving. Numerically, this is a very challenging one because there are meshing issues, and you're moving meshes embedded inside another meshing system. That can become very complicated. So our numerical simulations, we try to study what sort of flow is generated as I keep changing the blockage in front. And then we try to compute what sort of torques are acting on the body. And we can see that we could tell that there are optimal positions for these generators. So what we're trying to do is use mathematics and computations to come up with an optimal design for these objects. So the torque becomes very high, and at the right configuration, the torque on the object becomes very high. And also, which means that it will eventually generate high speeds of rotation. So there are certain kinds, we're trying to come up with a good design for a turbine. So I'll continue with a different example. This is just an example to show that some of these problems which seem to be meaningless, right? Who would think that dropping a little ball, or you drop something and it falls to the ground, you start to pay attention to it. It's a lot of very deep and complicated physics and mathematics into it. And then realize that there's even engineering problems and use this to help humanity. So, I mean, we were considering that even if we don't do anything big, we can use these to build microgrids, small scale energy harvesting from lakes and rivers. Okay, so how much more time do I have?
Yes, sir. Another 40 minutes are there, sir. 40 minutes. 10,
Okay.
10.
So the next problem I wanted to briefly discuss is the fluid dynamics of the eye. So this is a completely different problem, nothing to do with the previous case. And but a very beautiful and interesting topic. So here's an example in biology. So if you look at the human eye, so here's a cross section of the eye, but here's the eyelid, the lens of the eye, and this is the actual eyeball area. Now this portion is enlarged over here. So if you look at the eyeball, like this is the eyeball. I'm just making a small cartoon of it. On top of the eyeball is something called there's a layer of liquid sitting over here. But that liquid is quite complex. It's not as simple. The tears, which protect the eyeball, they're made up of 3 layers. One is a mucus layer, one is an aqueous layer, and then there's a lipid layer. So basically, mucus is something very thick. I'll talk a little bit more about this. Aqueous layer is more watery. Lipid is just oil. So usually, you find the lipid layers more on the open surface of the eyeball. This is to prevent evaporation of air. This is more watery, so when you cry and things, your tears come out and you can feel the texture of the tears. Mucus is something that sits very close to the eyeball, a very thick layer. But it's a very funny, it's a very gooey, elastic, light liquid. And so the question, once we heard some talk about this once, my colleague and I, we wondered, why do you need something which is elastic? How can it help the eye? What is the purpose of something like that? And the only answers we could find was that mucus is meant to protect the eye. Now, the body produces mucus in the various conditions. Our body is completely lined with mucus in the lungs, other parts of the body as well. So when you're cold, the body generates mucus as a way of releasing excess mucus in the body. But otherwise, mucus serves a layer as a protection layer because of its high viscosity. And I guess I also want, so in this picture, there's also the picture of the eyelid. And the eyelid is, the eyelid goes back and forth. So if your eye blinks, this is moving back and forth. And that generates motion. So the back and forth motion, when you're blinking, you don't even realize that our eyes are blinking. It is a automatic motion. When it blinks, what happens is it generates forces inside that causes the tear film inside the eye to move in a particular way. So the eye does very, there's different kinds of motions. One is voluntary motion, you move it yourself. You don't even realize, it moves by itself. Your tear film is generated constantly. Because your eye blinks even when you're not realizing that your eye, to clear out old tears and to coat your eyelid with new tears. These are regular sort of blinking motions. But then there's something called responsive blinking. This is something I'll talk about. Responsive blinking means when something goes into your eyelid starts to blink and flutter. So it's very interesting, and the human body is just a beautiful thing. There's so much to learn from simple things like that. There's very deep physics and mathematics hidden right here. And we know a lot about the properties of the eyelid. Biologists have studied these things quite a bit. Even though I have to say that we've been looking for more data on this, and some of it is hard to retain. But still, people have studied some of these things. So, this focus on important here. So, the purpose, if you look at a dictionary, a medical dictionary or something, it says the mucus layer contains proteins called mucins, and the purpose is lubrication and protection. So I can understand there's a thick layer over there. It's meant to protect any foreign objects from penetrating into the eyeball. So you need something very thick because the aqueous layer is just water. So anything can fall through water. If it's very viscous, it's very hard for it to penetrate. Like we saw in the very first picture that I showed you, sugar water syrup. It takes 22 days for a brass object, super heavy object, to go all the way through. And if you have even a small bacteria, virus, or whatever is trying to get through any foreign object penetrating your eye, then you need something thick coating to prevent. So I understand. So lubrication and protection. But what exactly is protection? Protection makes sense for a biologist, but for an applied mathematician, what does protection mean? And mucus is a very complicated liquid. So mucus has all these crossing fibers, these molecules come together and they have gel-like properties. So what exactly, how can something as complex as this, why do you need something as complicated? Why didn't the body generate simpler liquids? So mucus has far too many properties, physical properties. So here is a close-up view of the way the tear film looks. So here again, this is the cornea or the eyeball, and then there are these mucus is made up of. So I mentioned previously that there are 3 layers. Mucus layer, and then aqueous layer, and then lipid layer. Let's forget about lipid layer. So we'll only look at 2 layers. These 2 layers would be just the mucus and aqueous layer. Aqueous is just water. Mucus again is not just a liquid. It's these are proteins. There are different kinds of proteins. If you go even deeper and closer, you take a microscope and look at it, you realize that you cannot break up these systems into continuous systems. In the sense, in reality, what they are almost particular, special. Think of them as tiny spheres floating around in the system. So happens the density of so mucus is made up of mucin. Mucin protein is very heavily found at the bottom layer of the tear film. And there are a few free-floating ones that are found at the top. They get progressively lesser as you go to the top. So, in reality, this is a very complex system. In our models, what we tend to do is we have to simplify, because we cannot treat all of these. It's not too difficult to treat the problem in its full complexity. So, but it's good to know what it is we're dealing with. So, we know that mucin content is about 5 to 10% in the tear film, and water content is about 90%. So what we do is actually use this information to model our system as a homogeneous system, as mentioned. Now, why is this important? Why are you caring to study about these things? Because there has to be a purpose and a reason to study some of these things. And we found that trying to understand the mathematical function. So I haven't even told you what we're studying. So the question that's driving me is, what is the purpose of mucus as a protective layer to the eye? What kind of dynamics does it have? And how do you describe it? How do you mathematically describe it? So it turns out that there is great value in understanding this, because the motion of tear film in the eye is linked to all kinds of pathologies, called one in particular, called dry eye syndrome. This is when your body, your eye in particular, fails to generate enough tear films that can cause all kinds of ocular problems, and possibly even blindness. And so this is something that dry eye syndrome is something that increases with age and can become severe. So it's important to understand physiologically and biologically there is a reason why these kinds of studies happen. So we basically understood we looked at the properties of mucus and to create our models. One other thing. So the way that we want to understand protection, here's what we're thinking. Right? The question I'm asking is, how does mucus cause protection of the eye? What does protection mean? What is the mathematics of protection? What is the physics behind it? So let me propose this. It's a hypothesis that protection could be, if the first has protection against what? Then I might say protection against some foreign object that's attacking the eye. So imagine here's your eye. There's an object that's penetrating the eye. It's coming into your pupil. As soon as something enters your eye, natural reaction to the eye is for the eyelid to start blinking. It starts moving back and forth, back and forth. That generates a flow inside the liquid. How is the liquid moving? The liquid is moving back and forth, back and forth, back and forth. There are stresses generated inside. That is going to affect the foreign object that is entered the So the foreign object will move back and forth, back and forth, back and forth. So a hypothesis is that by the time the object interacts with the mucus layer, something is happening which is causing the foreign object to get pushed out. So somehow the foreign object is going to push out the object. So this is our hypothesis. We want to check it mathematically. Now, one thing we learned is one interesting thing happens. If you think of mucus in this form, now here's a human development. When a foreign object enters the paper, it interacts with these free-floating mucins, these mucin particles. And like it says over here, these are gel-forming mucins. These are mucins that will aggregate to form jelly-like substance. And here's a picture of something, this is from the kidney of a dog or something like that, but it's a very large, it's called a plug, a mucus plug. And you can even see something, I mean, not to become disgusting here, but in the morning when you clean your eyes, we find mucus trappings. And this is a way for the eye to clean out debris. So it's doing it voluntarily on its own. It's cleaning up, not blood, slug. Sorry. So from the intestine dogs. So this picture. So these mucin, free-floating mucins are capable of trapping or aggregating with foreign objects that penetrate. They wrap around them, they form these slugs. And so then you have, particle itself can be tiny, but you have this wrapping adhesion mechanism due to all different kinds of forces between them, leading to larger aggregates. And then when it becomes large enough, I guess the eye senses it and it starts to move and it causes all kinds of forces. So let's see what happens if we can predict this kind of, is the hypothesis correct? So we're asking, once again, I'll just repeat, what is the mechanism of protection? What is the purpose of elasticity of mucus? Isn't it enough to have a liquid which is just viscous? So this is what, so we built a little model, a mathematical model, where we said, okay, so a foreign body comes into the system. It's going to interact with mucin and lead to an aggregate formation. Then once it forms an aggregate, the eye will start blinking. The blinking will generate a flow in the clear film. But if your mucus is viscoelastic, then there is something called normal stress. So one distinguishing feature between a regular Newtonian liquid and a non-Newtonian liquid. So you remember the example I gave you of this rod climbing. So when you stir coffee, the liquid goes down. You stir viscoelastic liquid, the liquid starts to rise and climb onto the rod that's stirring. And the reason is because Newtonian liquid, the only kinds of forces that are present in the system are what are called shear forces. So if I take a layer of water and I move my hand this way, I'm shearing it, applying a certain horizontal force, and that horizontal force will translate all the way in. It's going to, the next layer will apply a slightly smaller force, slightly smaller force, slightly smaller force, so on. It penetrates through the depth of the liquid. So the forces, if I apply force like this, there is a similar force that goes down all the way. In a viscoelastic liquid, if I apply a horizontal force like this, not only does this force, a horizontal force penetrate, but there is a vertical force that is generated inside. Very absurd thing. But these are called normal stresses, perpendicular stresses which are generated. So then now you can see if mucus is an elastic liquid, there is no evidence for this from experiments. We're trying to prove this mathematically. But the idea is if I apply a horizontal force, your eye is moving back and forth, it's possible because mucus or the system contains elastic property, that the foreign particle, which is trapped now, the larger particle, will experience a certain upward thrust, which then get pushed up. So we have these models set up as these two phases. So phase one, so we're assuming that the particle is going to enter the clear film. All these mucins. As it interacts with the mucins, it gets trapped, it becomes an aggregate. It goes deeper, it becomes a bigger aggregate. At some point, right, so the effective radius of this aggregate will get larger and larger. At some point, the eye is going to start moving. And so how does it happen? We're assuming there's some sort of a chemical reaction, some van der Waals forces, some bonds that form between, so some foreign object X, a mucin particle to form an aggregate. And as the single aggregate binds with more mucin, it becomes a bigger aggregate. So we'll just take a very coarse model for this, take a simplistic model to understand this idea. So the aggregate is growing larger and larger. It means its radius is becoming. Assume that it's not always a sphere, but we'll assume that there is an effective sphere around of a certain radius. Now the radius of the sphere will change with depth as the object falls, interacting with more and more object, mucin, and it's getting larger and larger. So the rate of change of radius with respect to the depth, right, is proportional to the probability density function of the mucin. So how much mucin do you actually have? So there's some reaction rate, and then you can multiply it with the probability density function. So if you're assuming, take a simple example, that mucin is distributed in a constant way, so the probability density is 1. Same amount of mucin everywhere, it's constant. Then the radius grows linearly. So this process is called, this is our addition process, so it's just a simple example. So the radius grows like this, then the volume of your aggregate, the particle plus all the mucin that it's trapping around it, is going to grow according to this formula. So it's the radius of the original particle plus the extended thickness of the mucin. And then the density of this whole slug will grow according to a particular formula. So you can write a weighted density formula. And now what we do is these two, so this is part of the phase one. We're just, in a simple way, we're modeling how the aggregate particle is entering the clear film, is interacting with the mucin particles due to some van der Waals forces and chemical forces. And it's growing in size, and the rate of growth is given like this. The rate of volume goes like this. The density grows like this. This is the macroscopic reaction. This becomes an input to phase two, which is a macroscopic reaction. So once I know, also what's interesting is once I know the density and the volume, I can multiply and I get the mass. And I can see if I plot how the mass of this aggregate behavior changes, it goes non-linearly. So the mass is low and then it dips lower. Even though the size is growing, the density is not growing linearly. So it reaches some minimum and then it rises. Okay, so the phase two is a little more complicated. Now we have an aggregate object, certain size, sitting in a liquid. The liquid is moving in a complicated way. Now the question is, how is the particle going to be transported into this, due to the flow itself of the blinking? All right, so we've studied this in a couple of ways. I'll just describe, this is an earlier study. This paper was published 2014, 15 or something. We just finished another work where we take a slightly more complex version of this flow. So we take this kind of a geometry. So here you have, this is called a sliding bearing geometry. This is a flat base and it's slightly tilted on the top. Now, we don't exactly know, and I'm taking this to be the eye, essentially. So I'll take this to be the base of the eye, and this to be the eyelid. So this base can go back and forth, like a blinking motion. And I don't know if the eyeball and the eyelid are exactly parallel to each other. So we just decided we'll take different shapes. So the equations we want are again conservation of linear momentum. We need boundary conditions. We need other constraints. These are called continuity constraints or divergence spacing system, which means there is no accumulation of liquid at any point. Now, key here is what's called the stress tensor. Stress tensor describes the material properties of the liquid, what sort of forces, internal forces it is. So in a simple liquid, the only driving internal mechanisms would be pressure and viscosity. The pressure, internal forces generated within would be pressure and viscosity. In a non-Newtonian liquid or an elastic liquid, stress tensor is far more complicated because there is internal components of pressure, with viscosity. It also has elasticity. This is viscosity need not be a constant. Its elastic properties need not be a constant. So it could very soon become very complicated. So in our particular model, we wanted to understand, said before, there is some evidence that mucus, we're trying to model mucus, that mucus is a complex liquid. It is non-Newtonian, so we wanted to model a non-Newtonian system. So we take our model for the non-Newtonian to be this Maxwell type model. So it has pressure, it has a viscosity component, beta or mu is used for viscosity. Alpha 1 is, these are called normal stress components. So, alpha 1 and alpha 2, the two normal stress components. We also assume that beta, which is viscosity, is not a constant. As it flows, as the liquid flows, there is this changing shear forces within the system, and that's going to change viscosity. So overall, this is a very complex, very difficult equation to solve. So the point being, we didn't solve it exactly. We have to use approximation. So we applied these approximations for lubrication approximation, because ultimately what we're doing is solving the problem in a very thin layer. The eyeball, the eyelid, is just a few distance between the eyeball and the eyelid is only a few microns, which is very, compared to the length of the eyeball, the thickness is very small. So you can make these approximations for lubrication. And we make a few other approximations. And then we write down the components of stresses. And it turns out the velocity, you can find a solution to the problem where the velocity looks like a quadratic. It looks something like this. So you have a horizontal component of flow, there is also a vertical component. So overall, you can use certain tricks and solve these lubrication approximation equations by assuming conditions for the flow, boundary conditions for the flow, but you also have to have some constraints on the stresses in the system. There's some additional stress boundary conditions that you have to apply. And once you do this, you can actually write down the equation for the flow. And it turns out, so let me go back into my view. So we have one parameter called Q. Q tells me how there are different non-Newtonian parameters in the system. Q is one of them. So the more the Q, the more non-Newtonian. If Q is positive, then I have something called a shear thickening liquid. If Q is negative, I have a shear thinning. I also have alpha 1, alpha 2. These tell me about elasticity. So any information about alpha 2, alpha 1 also tells me about elasticity. But we also non-dimensionalize the system. So we can take our dimensions away from this problem to make it simple. And it turns out that we have Q is one parameter. Then you have this as a parameter. E is called the Deborah number. Deborah number tells you something about the elasticity of the system. So, and then we have another parameter called M. The M comes from the geometry, so it tells me how my eyelid is sloped. Slope this way, positive slope, negative slope, horizontal, M is 0, and so on. So we're interested in understanding the impact of these parameters also on the flow and the eventual result. So we assume values for these parameters, for different values, and that gives us, and we're able to solve exactly for the flow, and then we can graph it. So here are some numerical results. Once you solve them, you can numerically solve these things. And you realize, so here is the effect of elasticity of the system. Everything being the same, so M parameters taken to be in all of these is negative, so there's a negative slope. And at the bottom, it's all a positive slope. And the Deborah number is increasing, which means the elastic content is increasing. And you see the effect. When I increase the elastic content, profile becomes nonlinear. You can also see at the bottom, the flow is going faster and faster and faster. This is where the blinking is happening. This is where the eyelid is blinking. This is showing you one snapshot. Okay, so we're able to use these tricks and approximations to take a complex liquid, right, like mucus, and we're able to obtain the velocity profile. So I know what the velocity of the liquid is. I know the direction it's flowing in. I know what speed it's flowing, at what point, in space and time. Then the next question is, okay, so the big question is still, what we're after is, how is this liquid going to protect it? Yeah. Well, we decided what we want to check is, what does it do? What does the liquid do to any foreign object that's inside? So now that we've solved independently for the flow, the liquid, we have to see what the flow of the liquid does to any object that comes inside the eyelid. So now we write down, so imagine that you have some particle that enters the eyelid. Well, the flow is going to interact with the particle and generate forces. So then the next follow-up question is, well, how is the particle moving? So the forces, the net force on the particle will be, you can write that as a sum of various other forces due to the fluid. So the motion of the fluid will generate different kinds of forces. One is called the added mass. There's a force called the Bassett force, a force called the drag force, the lift. So the drag is a frictional force, lift is how much the rotation of the body will cause a lift force. And these are forces that are generated because the liquid is accelerated. In the flow, the liquid itself generates. And there are other specific equations. Right? So ultimately, the flow of the liquid is going to cause forces acting on any particle that's embedded in the system. And so then we solve this particular problem, this equation, using a second order unfettered method. We assume that certain boundary conditions for the system. We pick numbers for the various constants in the system. And some of these are inspired by biological data, but we don't always have data. And we ran some simulations for different paths. So the top picture here is, so you can see the left side is the eyelid, the right side is the cornea. This picture tells you the horizontal speed of the particle. This tells you the vertical speed of the particle. And this is the depth. And these are the drag forces and the lift forces. This is a complicated picture, but I think the main point to be noted here is so over here in this picture, I think that's, if I just look at this, there are some edge effects that happen in the computation, so these are not realistic. What happens in the middle is more realistic. We find that as I change in depth, the drag forces or the horizontal motion is about the same. Speed is the same. And it doesn't change no matter how much elasticity there is in the system. Even if I change the elastic content, nothing much happens. The drag forces also, you see this, some odd effects here, when things are zero. But otherwise, everything else goes in the same line. So that all the other forces almost behave similarly, even if I change elastic. But what really changes, the important change that happens, is the lift forces and the vertical velocity of the object. So you see the vertical velocity is a maximum when the Deborah number is 0.75 in the system, which means it's the highest. So the maximum acceleration in the system happens, the maximum change happens. The biggest gradient happens when elasticity is high. It means, and also the highest elastic forces, for the most part, are highest when the elasticity content. So what is this telling us? That if I increase elasticity in the liquid, the possibility of the particle, any foreign particle that's entering the clear film, so the possibility for that to get ejected from the system is high. So here is another, so basically we just measured the percentage change in the behavior, in the lift forces for various different conditions. We take different geometries of the system, take slightly different values of the different kinds of liquids, shear thinning, shear thickening. So no matter how I vary the liquid or the geometry of the system, I want to see what is the percentage change in the lift of the object. So if my object is moving like this, I want it to get ejected from this. I want to get, particle, if it's getting trapped, something is going near the cornea, eye starts to blink, particles get lifted up. So which one produces the greatest lift? And what you can find is as the elasticity increases, the lift value goes up. It's almost consistent. So the black pictures are the lift forces, and the white bars are the lift velocity. In either case, I think in this example, it's all monotonically increasing, except for this one observed case. And then we also
Ashwin sir, sorry for the interruption, sir.
Yes.
Sir,
No problem.
Another 5 minutes.
Yeah.
5 minutes.
Okay.
5 minutes, sir.
Thanks. Yeah, that's good time.
Thank you, sir.
So, in conclusion, I think I'll just say that what we found from our computations is that the viscoelastic nature of nucleus, this is our first modeling attempt in this problem, was to understand if clear film mucus is viscoelastic, then what exactly does it do? Right. So what we're finding is our calculations are showing us that if your clear film is elastic, the body enters, your eye starts to blink, that generates shear forces, so the particle moves back and forth, but because the liquid is elastic, there is also a normal force generated, and so the normal force then clears it out, and will bring it to the aqueous layer. The aqueous layer is now just a Newtonian liquid. The aqueous layer doesn't have an upward push, you just flush it out. So if you do a simple study like this, right, you're looking at a very complex system. The eye itself is far too complicated. So the beauty of mathematics is you can use existing model, make approximation, reasonable approximation, and come up with a good hypothesis for why something is the way it is. Why certain phenomena happen. And then, so this is telling us this particular calculation, this particular study told us something about the clearance rates of how does tear film get cleared in the eye? How does it protect the eye? And so we're trying to build on these studies, like making our model really more realistic and appropriate. So this is another study that I'm doing, has to do with brain disorders, but I think I don't have time to go into this. So I think I will stop right here. Let's get to the last. Thank you very much.
Yes, sir. Yes, sir. Thank you, sir.
Thank you for your patience and
Ashwin Garu, it is a wonderful time with you, sir. Highly thought-provoking session, and definitely, sir, we have nearly 500 participants in this FDP program, sir. 500.
Is that right? 500?
Yes, sir. Yes, sir. Yes, sir. Definitely.
That is fantastic.
I thought that thought-provoking already started, but the examples you have considered, no, sir, very typical examples, and how we can deal those fluid flows and make a mathematical model and come out with the solution. Great, sir. Really, hats off to you, sir, for your research.
Thank you very much.
Wonderful time with us, sir. Thank you.
Absolutely.
And thank you for your valuable time for sharing with us, sir. And thanks to our Murali Mohan also, our faculty Murali Mohan,
Absolutely. Many
for
thanks,
giving
sir.
us a wonderful person in this. Really, you added a value, great value to our faculty development program, sir. Thank you very much.
Sir,
Yes.
thank you, sir, Ashwin, sir.
Absolutely.
Thank you very much.
so much.
And it's
Thank you.
each and every slide very informative.
Yes.
Live simulation.
Yes.
I hope completely simulated the slides
Right.
where I observe.
Murali, you have used the right word. Huh?
Yes, sir.
Live simulation, like.
Yes,
Very
sir.
good, very good.
Thank you, sir. Thanks for accepting our invitation, and you have given your time, sir. It is almost midnight for you, but still you have given so much.
Very excited and happy to be here.
Yes, sir.
We were eagerly waiting from yesterday onwards, sir, when we will need to.
Ashwin Garu,
And thanks,
you have got very good response, sir.
Go ahead.
I will meet you through email, sir, once again.
Okay.
Thank you very much for your valuable time, sir.
Absolutely. Thank you so much.
Namaste, sir.
Best.
Thank
And
you.
I thank you, Ravikant sir, Professor A.S. Ravikant sir, and Kurukshetra. He is joined in your session, sir.
Sir, namaste, sir. Namaste. Ravikant Garu, namaste, Andy. Namaste.
Namaste. Namaste.
Ravikant Garu also in this session, sir, in our same room only.
I see you. Yes.
Almost after 10 minutes or so, from beginning after 10 minutes, sir joined with us.
Okay. Yeah, I didn't see him before. I see his name now because my whole screen was covered, so I didn't know who's here.
We really enjoyed, sir.
Thank you very much. It's very nice to be here, and
Thank you, sir. Thank you, sir.
thank you.
Thank you.
See
sir.
you, sir.
Thank you.
Thank you.
See you, sir.
See you. Bye, everyone.
Thank you very much, sir.
I said good night, sir.
Good night, sir.
Good night.
See you, sir. Good night. Gupta Garu, please give your vote of thanks, sir.
Good morning, all of you.
Yes, sir.
So the 5-day online international faculty development program, I would be very much privileged to propose vote of thanks. which was conducted from 25th to today because of 1 day gap because of yesterday some unseen difficulty. So anyway, any good event comes to an end. So this event has also come to the end today. On behalf of mathematics group of GMRIT, I propose the vote of thanks for all the following people. First and foremost, I thank our management for providing necessary facilities to conduct this international FDP for 5 days duration. I thank our principal of MRIT, Dr. LVRS Prasad, the person behind all of us for motivating us to conduct this online FDP. I also thank our Vice Principal, Dr. Raja Murugadas, for his continued support and guidance. The man who encouraged us to conduct this FDP is our HOD, Dr. R.L. Naidu. I thank him for continuously supervising and getting all the technical support from other people of GMRIT. I wholeheartedly thank all the speakers of this FDP who readily accepted our request in spite of busy schedules. The international speakers are Dr. V.G. Naidu from Ethiopia, Dr. Ravi P. Agarwal from USA, and today's speaker Dr. Ashwin Vaidya from USA. The national speakers are Dr. M. Kishore Kumar from BITS Hyderabad, Dr. V. Ravindranath from JNTU Kakinada, Dr. T. Panindra from VIT Well, Dr. D.V. Vision Tech Hyderabad. I thank all of them once again. It is a teamwork of our entire mathematics group whose continuous efforts made this FDP a grand success. I thank all of them. In particular, Dr. Sumati Kumari for coordinating on all the days, Dr. Murali Mohan Kumar for his continuous technical support, Dr. Seshaya sir for monitoring all speakers and bringing out any questions and so that the speakers could answer them well after the sessions are over. I thank once again our whole team. Thanks are also due to all the people who involved directly or indirectly made FTP to happen very smoothly. Last but not the least, I thank all the participants from various parts of India as well as across the globe for sparing their valuable time and participating in the FTP. Even though 1 day was delayed because of some, as I told you, some problems at USA, still the participants enthusiastically participated today's day also and gave very good feedback to organizers. I thank once again very much. For all the participants who sent the feedback regularly, the e-certificates will be sent to their emails shortly. Okay, so once again, thank you all of you at home during this time. So thank you once again. I'm Gupta signing off.
Thank you, participants. స్టార్ట్ చేద్దాం అనుకో చేసి ఫీడ్బ్యాక్ 20 minutes బిఫోర్ ఇచ్చాను స్ట్రీమ్ ఏం చేస్తాను